Welcome to the deep dive. Today we're plunging into a stack of sources that could, well, fundamentally shift how we think about life beyond Earth.
That's right.
Our mission is to unpack how something as violent as a cosmic collision might actually be the secret architect of atmospheres, maybe even habitability on distant worlds.
We're exploring a really fascinating news study. It's from the University of Leeds, and it asks this bold question. Could icy comets be the unsung heroes?
Heroes how?
Delivering the crucial ingredients for life to exoplanets,
Mm-hmm.
Much like the theories suggest happen for our own Earth.
Okay, so we're going to delve into the specific mechanisms here and the surprising ripple effects of these impacts.
Yeah, the details are quite something.
So you can walk away not just informed, but maybe with some genuine aha moments about these cosmic forces shaping planets.
Hopefully.
So let's set the stage. Let's look at our own planet first. Earth became this vibrant, life-bearing world because, well, as the sources put it, a billion events had to align perfectly, just right.
Mm-hmm. A lot had to go right.
And a crucial part of that cosmic lottery win, was an early bombardment. Rocks, icy bodies, delivering the water and organic molecules essential for life.
Absolutely fundamental.
Without those ancient impacts, Earth as we know it simply wouldn't exist. It'd be a very different place.
That really does highlight a powerful idea, doesn't it? I mean, if this process was so absolutely vital for Earth, for us,
Yeah.
then it really begs the question, could the same cosmic delivery service be the key, to unlocking habitability on distant exoplanets too?
That's a great lead-in. So if we are looking for exoplanets where this kind of cosmic sculpting might be happening, where are scientists actually focusing their gaze?
Well, a lot of attention is on M-dwarf stars.
The small, cool ones.
Exactly. Smaller, cooler, dimmer suns.
Yeah.
And they often host numerous rocky planets, often in incredibly tight orbits, really close in.
Okay.
And what's particularly interesting about many of these planets is that they frequently become, well, tidally locked.
Ah, right. Like our moon is to Earth, always showing the same face.
Precisely. One side is perpetually bathed in starlight. The other side, eternal night. Pretty extreme conditions.
Why does that specific characteristic matter so much for studying habitability? I mean, it seems kind of counterintuitive picking such an extreme world.
It's a great question. And it's actually brilliant for the research side of things.
How so?
Tidally locked worlds, they eliminate some major uncertainties. Things like the planet's spin rate, its axial tilt, those are fixed.
Ah, okay. Less variables.
Exactly. So it allows researchers to model climate and weather patterns with incredible precision, much more focused.
I see.
We become ideal, sort of simplified laboratories for these really complex stimulations. It strips away a lot of the noise, letting them really isolate the effects of, say, an impact.
That makes perfect sense. Okay, so with that in mind, let's explore the core of their source material. These groundbreaking simulations from Felix Sainsbury-Martinez and his team at Leeds.
Right. So they modeled a very specific scenario. They asked, what happens if a pure water ice comet hits one of these planets?
Pure water ice.
Yeah, specifically one with about a 2.5 kilometer radius. So, think the size of a small mountain, and a density like solid ice.
Okay.
And they aimed it, virtually speaking, at an Earth-like, tidally locked exoplanet. The model itself was specifically based on TRAPPIST-1.
Ah, TRAPPIST-1. That's a famous one. Known for possibly being rocky and in the right zone.
Exactly. It's a prime candidate for habitability studies because of its intriguing characteristics and its location in that system.
Got it. And what exactly did their 3D Earth system model show? What happens right after this dramatic impact?
They found two really significant things. First, most of the cometary water, it doesn't just splash down or immediately vanish. It tends to linger.
Linger where?
Up high, in the upper atmosphere. This happens because of something called thermal ablation.
Thermal ablation. Sounds technical.
It just means the intense heat of the impact vaporizes the ice. Oh. Right. But then the lower pressure way up in the upper atmosphere allows that water vapor to just hang around, almost like a persistent high-altitude cloud.
Interesting. And the second finding?
The second thing was that while the impact energy certainly warms and expands the mid-atmosphere, surprisingly, the effects on the surface remained minimal.
Really? Not a global inferno?
Not according to these models, no. Which is quite counterintuitive.
That is fascinating, that the surface isn't dramatically hit. But, okay, this leads to a critical question for actually finding this, right, for observation. Could we detect these unique signatures? This lingering water vapor maybe, or the changes high up?
That's the million-dollar question, really. Could our telescope see this?
And once that water vapor is injected up there, I assume it doesn't just sit there passively. You said it kicks off reactions.
Oh, absolutely. It becomes a powerful chemical catalyst. That water vapor quickly starts transforming the atmospheric chemistry.
Like what?
Well, for instance, the UV radiation from the star acts like tiny scissors. It splits the AgO molecules into individual hydrogen and oxygen atoms.
Okay.
And this then helps or fosters the formation of other molecules, things like methane CHO and nitrous oxide NUO. Both are incredibly potent greenhouse gases.
Right, they trap heat.
Exactly. And another effect is that these free oxygen atoms, they can combine to form things like NOA, nitrogen dioxide.
That does.
That acts like a wrecking ball for ozone. It destroys ozone, which is often seen as a key protective layer.
Wow, okay, so it's a complex chain reaction.
Very much so. And then remember the tidally locked nature. On the perpetually cool night side, that extra water vapor can condense. It forms ice crystals, clouds.
And those clouds would reflect starlight.
Precisely. They scatter incoming starlight, further influencing the planet's energy balance. It's a whole atmospheric cascade.
So these aren't just fleeting, momentary effects right after the impact. How do these chemical pathways, the new molecules, the clouds, how do they reshape the climate over longer timescales? We're talking decades now, not just days or weeks.
Yeah, the simulations looked at that too. They revealed that even a single icy impact can have significant multi-year consequences.
Like how long?
It can enrich the water content in the mid and upper atmosphere for well over 10 years. That water sticks around.
A decade or more from one hit.
Yes. And it can also subtly shift the annual temperature oscillations. These are influenced by the planet's layout, land versus ocean, and the uneven heating from the star.
Okay.
And here's a really surprising detail, I think. They found it could even cause up to a 2 Kelvin surface cooling on the day side.
Cooling, not warming from the impact.
Cooling, primarily because that added water vapor and the extra cloud cover makes the atmosphere thicker, more opaque. It blocks more incoming starlight from reaching the surface.
Huh. Just a couple of degrees, but on a planetary scale, that's significant.
Absolutely. It could drastically alter conditions, even if it sounds small.
Those multi-year changes, they really hint at much longer-term climate feedbacks, don't they? It really makes you wonder, what if impacts like these weren't just isolated, rare events? What if they happened regularly? Especially, say, during a planet's early formative years.
That's exactly the right question to ask. Because while the immediate post-impact effects are clear in the models, they actually fall below the detection threshold of today's telescopes, like James Webb, after about a year.
So they fade relatively quickly from our view.
From our current view, yes.
Yeah.
If we were to look, we'd likely miss the signs unless we were incredibly lucky observing right after an impact.
And these events are pretty rare in a mature system like ours, right? Not happening all the time.
Indeed. The estimates are maybe once every 190,000 years or so for a typical Earth analog planet.
Wow.
So yeah, spotting one in real time, that would require truly exceptional luck. Or, the next generation of space observatories, things beyond Webb.
It's like trying to catch a single raindrop in a hurricane, but you only get to look for 1 second every few centuries.
Something like that, yeah. The odds aren't great for catching one live.
Okay, but this brings us to a really crucial point then. Young planetary systems, they experience far, far more frequent impacts, right? That early chaos.
That's the key insight, I think.
Yeah. This early, repeated, icy bombardment, that could be the real game changer for habitability. This is where it gets really thought-provoking.
Precisely. Cumulative impacts, lots of them, happening relatively close together during a planet's chaotic youth that could fundamentally drive long-term climate restructuring.
Making it habitable or?
Potentially enabling life as we know it. Or, fascinatingly, maybe even inhibiting it. It could go either way depending on the specifics, the frequency, the size of impacts, the initial atmosphere.
It's not necessarily always good news.
Not necessarily. But it also leads to significant chemical enrichment of atmospheres. You're delivering water, yes, but maybe also essential volatile compounds, organics, basically setting the chemical stage.
This truly raises a profound question then. Could some exoplanets we currently look at and maybe dismiss as uninhabitable, could they actually be perfectly life-friendly or on the path to it if only we could see them at the right evolutionary stage?
Right, if we could somehow glimpse them during their incredibly impact-rich youth.
Yeah, it shifts our whole perspective of what makes a world habitable now versus what its history might have been.
It really does. Maybe habitability isn't just a static state, but a phase influenced by this violent history.
So this deep dive into the University of Leeds study, it really underscores how these icy cometary bodies, they aren't just space debris floating around.
Not at all.
They are powerful sculptors of planetary atmospheres and potentially the very conditions for life itself.
And while a lone impact, as we said, leaves detectable marks only briefly with current tech, it's the cumulative effects.
Yeah.
The early, frequent bombardment over millions of years that may actually make or break habitability on distant worlds.
It's the long game.
It's the long game, played out over cosmic timescales.
And future telescopes, maybe specifically targeting observations of very young planetary systems, they could be truly revolutionary.
Absolutely. They might finally reveal these ancient cosmic footprints, the evidence of this early shaping.
And as we consider these powerful, really quite violent cosmic events, it does reshape our understanding of life beyond Earth. It hints at a much more dynamic, maybe even chaotic path to habitability than we sometimes imagine.
It's not necessarily a gentle process.
Definitely not. Makes you wonder, doesn't it? Could the key to unlocking the habitability of distant worlds lie not just in where they are now, their current state, but in the chaotic, impact-filled history they endured billions of years ago?
Looking back at their planetary childhood, so to speak.
Exactly. It's quite a humbling thought, isn't it?
It certainly puts our own planet's history into perspective.